Yes, no. Okay, so welcome to my talk, investigating perovskite film formation using optical in situ spectroscopy. First of all, why are we interested in the film formation at all? Well, in these kind of semiconductors like perovskites or organic semiconductors, the structural properties are well related with the optoelectronic properties, and the optoelectronic properties, of course, are decisive for the device performance. However, during the film formation, so in the case of perovskites, the material just forms before you've just the adducts. Perovskite forms only during the film formation. So obviously the film formation is also decisive for the device performance. So if we understand the film formation better, we can better control the film formation, and this enables us to achieve targeted optimization of active layer properties. And hopefully it helps developing or adapting new processing methods to new materials, and it will enhance the reproducibility, especially from lab to lab. So talking about the film formation, there are many aspects which can be considered. It's starting with precursor treatment, then of course the coating itself, for example, spin coating, but also post-treating like thermal annealing. We focus so far, or I focus today on the coating itself, especially on the spin coating, and we monitor that with optical in situ spectroscopy. That is, simplified, we have our coating device like a spin coater, we have a white light source, and then we have a laser, and we are then able to record absorption and PL during the spin coating quite fast. We do that frame by frame. So here in the upper panel, it's the case for a PL frame. The white light is off, the laser is on. The emitted light from the sample is collected via an optical fiber, let into a detection system. You have here a chopper wheel, and the light passes through this chopper wheel through a filter, which filters away the laser wavelength, and is then led with these two mirrors to a spectrograph. For the case of an absorption measurement, the laser is off, the white light is on. This chopper wheel is in such a position that the white light is reflected to the spectrometer directly without this extra beam path. So by synchronizing laser, white light, chopper wheel, and our detector, which is a CCD camera with a spectrograph, we are able to record absorption and PL frame by frame with a frequency of about 11 Hertz. Okay. Sometimes we also have some structures in our films which do not absorb or emit light in the visible range. But if they form structures that scatter light, we can still record that. We added, therefore, an extra LED. And you simply can record the intensity of this LED additional to the PL and the absorption. Okay, now let's go to an example. How do these spectra look? What can we get from the spectra? A simple coating of this perovskite is a one-step coating, and look at the one-step coating of MAPI from DMF solution. One-step coating is simply you have all your adducts in a solvent, DMF, you spin coat it for a certain time, you end up with a film. So for this system, it is known that the resulting film is not very nice. We have this needle structure here, which form, this is a solvent complex phase, so solvent molecules form a ordered structure with the adducts MRE and PBI2. And these solvent structures are then partly transformed to perovskite. Okay, for this coating, the typical spectra that we get look like this. We have here the photoluminescence as a function of time and energy, displayed as a heat map. We have here the intensity of this additional LED, so the scattered light. We have here the optical density. And we see already from this heat map that quite a lot is going on, but it's hard to tell in detail what's happening. So it is useful to have first a look at some spectra at specific times. Let's start with the optical density. And my cursor is a little bit Never mind. Okay, so let's look at the spectra here before anything is apparently happening in the map. This black spectrum up here, it is rather flat, but we see some kind of modulation. And this modulation it's not just a noisy background or something, but this is a signature of white light interference at the solvent layer. So depending on the thickness of the solvent layer on our substrate during spin coating, and depending on the wavelength, we can either have positive or negative interference, leading to a decrease or increase of the optical density. Now, if you know the refractive index of your solution that is on top of the substrate, you can calculate the thickness of the layer based on the distance of this maximum. If we look at this part a little bit in more detail, plotted in, again, as intensity heat map, we see that these patterns evolve during the coating. And just by taking basically the distance between two maxima, we can estimate via this formula the thickness of the solvent layer during the spin coating, which is quite nice. Okay, going to the next spectra, this orange one and this blue one here, they are, well, rather flat spectra, a constant offset in the absorption. This is the signature that some scattering objects form in the light path. And we know from the final film that this is basically due to the formation of the solvent complex phase in this needle-like structure. And then only slowly at later times, the spread spectrum here, we see the evolution of the absorption edge. This is basically the formation of the perovskite then. What you might see from this flat shape of the absorption, which does not really look like the absorption of a nice final film, we can see that we have only a partial coverage of the substrate, which is for this system not surprising. As I mentioned, these needle structures form. And if you are interested in this a little bit more, there's a nice work by Tian and Cheplikin, which discussed the influence of the coverage of the substrate on the resulting absorption spectrum. You can, in principle, also treat this and estimate from the spectra that we see the coverage and the thickness of the perovskite layer. However, put it a little bit short, the values that we can extract, just moderately agree with the final values which are indicated here with these boxes. Okay, so far to the absorption. Now let's talk about the photoluminescence. Again, looking at the same spectra, so at the very same times, this black one and the orange one, we don't see any PL at all. Then for the blue one, we see here a broad peak at comparatively high energies. So normally for a final film, we would expect it to be around 1.6 eV. And during the spinning, this peak shifts to lower energies, gets narrower, and increases. So this is a signature of quantum confinement. If the domain size, or in this case, the crystal size, is on the order of the spatial extent of the excited state, the excited state becomes confined and behaves very similar to the particle in the box model from quantum mechanics. And you may know from this particle in a box model, the energy levels and also the distance between the energy levels depends on the size of the box. And likewise, there's a formula to describe the PL peak position, which is simply the value of the bulk PL, so where the bulk PL is, plus some constant over d squared, with d being the size of the crystallite. So from the peak position, it is possible to extract something like the average grain size. From the shape, it is also possible to extract something like a grain size distribution. Now, looking at the evolution of the grain size with time, we can get growth rates. And in this case, we saw here first fast growth and at later times a slower growth. If you're a little bit more interested in this, it is discussed in more detail in this work by Christopher from the Eva Herzig group. Okay, now we have looked at the spectra quite in detail. To quantify the dynamics of the film formation, it is very useful to consider time traces of the different optical quantities. So here shown as a function of time, the intensity of the scattered light from this additional scatter LED, the optical density right above the band edge, and delta OD, it's basically how big is this band edge that we see. Okay, looking at these time traces, it is possible to identify different phase formation. So the first one is here at the moment where the scattering increases in both the optical density and the C scatter. This is what we can associate with the formation of the solvent complex phase. Then we have here in the optical density again a small increase, very subtle. This could be either due to more scattering or to absorption in the signal. But looking at the intensity of the scatter LED, we see a clear decrease of the signal. So we definitely have here absorption. And this is also the part, the time where we see the first PL signal. So we have here a first stage of perovskite formation, where the dynamics then change to a slower growth, the second stage of perovskite formation. We can also then quantify the timings and the widths, for example, by taking the derivative of this curve and fitting a Gaussian to the resulting peak. Yes, so now that we have the tools to analyze the data, I want to go to a recent example. It's a recent study from Simon Biberger from our group. He investigated the influence of the ionic liquid on the film formation. So ionic liquids are used to passivate perovskites, so to improve their optical properties, basically. And to investigate the influence of the ionic liquid on the film formation, we looked at solutions with different ratios of the ionic liquid. And we also, since with the one-step processing, we get these, not so nice films, we also had a look at the solvent engineering method. The solvent engineering method is a modification of this one-step processing, where the formation of the solvent complex phase is inhibited by adding a so-called anti-solvent after certain times, which forces the adducts to crystallize mostly in a very smooth way. So to know when we need to drop the anti-solvent, we need to know when the solvent complex phases form, and it is so we first had to check whether the ionic liquid influences the formation of this solvent complex phase. So analyzing the data of this processing for the different ionic liquid contents, as I just have shown you with the example data, we can extract the time when this solvent complex phase forms, and also the time when the perovskite forms. And the width of these boxes is a measure for the time that it takes to form this crystal. You can also extract the growth rate from the PL peak position. And what we now see for the different concentrations of ionic liquid is that the formation of the complex phase is largely unaffected. However, the perovskite formation is delayed and slowed down by the ionic liquid. This is also reflected in the lower growth rates that we get with higher contents of ionic liquid. However, what we wanted to see is the complex formation is nearly the same for all ionic liquid concentrations, so we can choose the same times of anti-solvent dripping for all samples. Since the film formation depends on when you drop the anti-solvent, we wanted to investigate different timings, which is 6 seconds, 12 seconds, and 50 seconds after spin coating. The spectra during the coating for the solvent engineering, shown here, if again the photoluminescence, the function of time and energy, the scattered light, and the optical density. And you might see directly that these look completely different from the one-step processing. So here, this white light, a white line indicates the moment where we add the anti-solvent. And right at this moment, we get already a very strong PL signal. This scattering signal from this additional LED vanishes completely, and we get a quite nice and structured optical density. Looking at the spectra of the optical density, these are shifted vertically for clarity. These are the first few frames after adding the anti-solvent. We see here a flat baseline, so we have no scattering, then something like a kink, and then an increase of the absorption. So this is the signature of the formation of small quantum confined perovskite crystals with a certain distribution. I think this is quite nice to see. So no scattering, so we have obviously a formation of a quite homogeneous structure. Okay, now looking at the growth dynamics, we have here the crystallite size extracted from the PL as a function of time for the reference solution, so without ionic liquid, for the different timings of the anti-solvent dripping. So here 6 seconds, 12 seconds, and 15 seconds after the spin coating. And what we see is that for later dripping times, the growth rates are way slower than for this 6 seconds dripping time. Why is this the case? Looking at the absorption in this high energy range around 2.8 eV, this is the energy range where some precursor states absorb, so the Udo-Brumbat, like PBI4 or something. You see at first the corresponding signal decreases. This is because material is thrown off from the spinning substrate. But then this peak increases again. This can only be if new material, new PBI4 minus or 2 minus is formed. So we have a change of the precursor states here during the spin coating as the solvent evaporates. You can also see this in the spectrum. This again, simply the optical density in this energy range. For this, close to this 6 seconds is this black curve here. Then for 12 seconds, this peak is already higher. And at 14 seconds, it's even higher. So very likely, the change of the growth rates is due to the difference in the precursor states. Now let's look at the effect of the ionic liquid, which we initially were interested in. For the case of the anti-solvent dripping of 6 seconds, we see again that the growth rate is reduced with more content of ionic liquid. With here the red one, the 1%, the one, the 5%. And this is also true for the other dripping times. Now, again, looking at the evolution of precursor states, we here the optical density integrated in this range where this PBI4 to minus peak absorbs. As a function of time, we have at first this decrease because material is thrown away from the substrate, and then this increase because more of the species is formed. It is a little bit a pity that we don't have access to the concentration directly, but what you can see is for one timing, for example, for the 6 seconds, the higher the optical density at this energy, the slower the growth rate is. This is also true for the 12 seconds. Here, the black one and the red one are quite close together. Also, the corresponding growth rates are quite close together. So this suggests that the interaction of the ionic liquid with precursor states in the solution, even before the film forms, are likely to change the crystallization dynamics and also the final film properties. Now, to verify this, let's do some cross-check with ex situ characterization. As you may know, if we put MAI and PBI2 in the solution, they don't stay MAI and PBI2, but they are rather present in something like Ma plus and some Udo-Brumbat complexes like PBI4 2 minus. And now, one way to check the interaction of the ionic liquids, we have ions here, we have ions here, is to do solvent NMR. In this case, they were performed by Helen Grüninger, also from the University of Bayreuth. And what we see from the fluor NMR probing this BF4 part of the ionic liquid, we always get an upfield shift if MAI is in the solution. So this BF4 interacts with the MAI. And likewise, if we look at the HNMR, or probing the alkyl part of this BMIM part, or the lead MMI probing this European blood species, we get an upfield shift when lead is in the solution. So this part, this BMMI plus, interacts with this PBI or minus, or with this European blood complexes. So indeed, we have an interaction of the ionic liquid with the precursor states, which is responsible for the change of the growth rates and the crystallization dynamics that we saw. Now, how does this affect the final films? So first of all, this ionic liquids is supposed to passivate the film, so it should improve the optoelectronic properties. So if you look at PL or the final film, as expected, the PL intensity increases from the reference solution to the 1% ionic liquid to the 5% ionic liquid. And this can be also seen in the time resolved PL, where we see a slower decay for high ionic liquid contents. So passivation works. That is nice. And looking at XRD by Nico Leupold, also from the University of Bayreuth, we see a decrease in the grain size, which is not what we want actually, because it was reported in the past that small grains really show higher non-radiative losses, and for solar cells we want the big grains. But we see also a decrease of strain in the grains, which is good for improved stability of the sample. And the smaller grains we also see in SAM measurements. So here's the reference film, quite big grains, and they decrease with increasing ionic liquid. Possibly the size of the grains is also related to the crystal growth rate. So it might be that there's room for improvement to change the processing in a way to speed up the crystallization for this high ionic liquid content. Okay, with that, I want to summarize my part at first, specifically on this part with the ionic liquid, how the ionic liquid influences the film formation processes. We saw that the ionic liquid already interacts with the precursors in solution, but it has surprisingly no impact on the formation of the solvent complex phase. However, it somehow delays and slows down the perovskite growth. And as a result, we get smaller crystallites with more ionic liquid, which might ask for adaptation of the processing for further optimization. Now, generally on the optical in situ spectroscopy, the optical in situ spectroscopy relies on the known relationship between structural and optical properties. So if you don't know this relationship, we cannot interpret the optical properties. It is a cheap yet powerful method for investigating the film formation, so how final film properties emerge and how they can be manipulated. And overall, this method has a great potential for inline monitoring and also inline control, because you can basically evaluate some of the optical properties during the processing and adapt the processing accordingly. However, you also need to be careful because too much light can alter the film formation. So the simplest example would be like laser heating. If you shine on it too intense with the laser, the sample heats up, and this changes, of course, the film formation. Okay, with that, I want to thank the whole perovskite group, all collaborators that took part in the work that I presented. Simon Bieberger, who did most of the work of the second part that I showed you. And I want to thank you for your attention, and I'm open to questions.